Good morning, students. So in the previous classes we have been discussing the MSP430 architecture. So let us continue the discussion on the architecture of MSP430 microcontroller. So in the last class we have seen the central processing unit of the MSP430 microcontroller. Okay. So this central processing unit of MSP430 microcontroller has a 16-bit ALU, arithmetic and logical unit. As you can see here, it is a 16-bit ALU. It can handle 16-bit numbers or 8-bit numbers also. Okay, so this CPU has this ALU and a set of registers. Okay, as you can see here, there is a set of registers available for handling the numbers. So the registers are from R0 to R15. So totally there are 16 registers. And each register is a 16-bit register, as you can see here, bit number 0 to bit number 15. Okay, and these registers and this ALU, okay, it is connected to what? The address bus, 16-bit address bus and a 16-bit data bus. Okay, now let us go through these registers one by one in detail. Okay, so here the first top 4 registers, as you can see here, for R0, R1, R2, R3. Okay, so they are used for some special functions. Okay, as you can see here, this R0 register is used for it is used as the program counter. Okay, so what is the function of this program counter? As you know, when we write a program for any microcontroller, okay, for example, if I write a program for MSP430 microcontroller, the instructions will be stored in the memory. Okay, then when any one particular instruction is getting executed by the microcontroller should fetch the next instruction that has to be executed after the current instruction. So the address of the next instruction that has to be executed next will be placed in this program counter. So this program counter always holds the address of the next instruction that has to be executed by the microcontroller. So as you can see here, the LSB bit of this MSP430 microcontroller is the program counter is always set equal to 0. That means this program counter, okay, the address in this program counter will always be an even number. Okay, so in MSP430 the instructions may occupy 1 byte, okay, or 2 bytes. Okay, so like that, always the address in this program counter is an even address, as you can see it. So the LSB bit is always hardwired to 0. So it is always be 0. Okay, so the address always that is present in a program counter while fetching the instruction is an even address. Okay, so that is about your program counter. Okay, PC. The next register is the stack pointer. So this R1 register can be used either for storing the data or for the stack purpose, to access the stack, but usually it will be used for stack purpose. Okay, to access the stack. Okay, so let us see how this stack pointer is used in case of your MSP430 microcontroller. Okay, so as you can see here, again this stack pointer LSB bit is always equal to 0. That means the address in this stack pointer register is always an even number. Okay, so let us see how the stack pointer can be used to access the stack. Now assume that this is the memory of my MSP430 microcontroller. Okay, this is my memory. Okay, so these are the memory locations. These are my memory locations. Okay. These are the memory locations. So this is my memory. Okay. Now, while writing the program, I want to use, assume that I want to use this part from here to this part. I want to use it as my stack. I want to use this location of the memory as the stack memory. Okay, then how can we use that as a stack? So for that we have to set the stack pointer register first. Okay, so assume that the address of this is this location from where I want my stacks to be sorted is 100. Okay, so this is 99th location and this is 90, this is 98 and this is 97. So like this, each location in the MSP430 memory can store an 8-bit number. Okay, so now I want to use this as my stack. Okay, this part of the memory as stack pointer. Okay, stack. Now the address of this location which is above the stack is 101. Assume that it is 102. Okay, now whenever I want to use the stack in MSP430, first I have to initialize my stack pointer. Now this is the part of the memory which I want to use it as a stack. So what I should do, I should initialize my stack pointer 2 locations above the location from where my actual stack starts. So here I will set my stack pointer register equal to 102. This is the address. Okay, so these are addresses left side. Okay, so each location can store an 8-bit number here. Okay, so here this location can store 8-bit number, this location can store 8-bit number, this can store an 8-bit number. Like this, every location in the memory can store an 8-bit number. Okay, now what I want here, I want to use starting from the location 100 onwards, all this part I want to use it as the stack memory. So for doing that, what I should do, I should initialize my stack pointer first. So where I have initialized my stack, I have initialized my stack pointer to the starting address 102. Okay, not to 100, but I have initialized to 102. Okay, so let us see how the stack can be used. Now whenever I want to use the stack, if I want to place something on the stack, I should write the instruction push. Okay, so what I'll write, I want to push a 16-bit number. So what I'll write here, 1 2 hash 1 2 3 and 4. Okay, so I want to store this number onto the stack. So when I write this push hash 1 2 3 4, okay, how this will be done by the microprocessor, okay, microcontroller. This what it will do, whenever I write this push instruction, okay, so the microcontroller will increment the stack pointer by 2. So now it is pointing to initially 102 stack pointer. Now this will be decremented by 2 first. So this is 102 minus 1, 101, then minus 2, 100. So the stack pointer will be pointing to this location. So the stack pointer, new stack pointer address will become 100 now. So whenever I say, okay, push, okay, whenever any push instruction is executed, the stack pointer will be decremented by 2 first, then this number, whatever the number that you have written here, okay, so here I have written the number as 1 2 3 4. So this number, okay, it will be stored in the memory. So here it will store 1 2 and 3 4 like this. So first 160-bit number will be stored onto the stack. Now if I write one more push instruction, so I will write here push. Okay, so I will write push, okay, hash 15A6. So if I write like this again, now again what the microcontroller will do, it will decrement the stack pointer by 2 first. Okay, now where my stack pointer is pointing, my stack pointer is pointing to this location, that is it is pointing to the location 100. This 100 will be there in this stack pointer. Now what it will do, it will decrement this stack pointer by 2. So 100 minus 2, it comes out to be 98. Okay, so my stack pointer new address will be this location. The stack pointer will go to this location SP. Okay, now this number 15A6, so this will be stored into the stack 15, okay, A6 like this. So as you can see here, okay, each location can store an 8-bit number. So even though it is a 16-bit number, they will be divided into 2 8-bit numbers like this while storing onto the stack. Okay, so this is how the stack push operation takes place. Now already the numbers have been stored into the stack. Okay, so every time when I push the numbers onto the stack, okay, stack pointer will be decremented by 2 first, then this 16-bit number will be stored onto the stack. So here as you can see what is happening here, every time I go on pushing the numbers onto the stack, the stack pointer address is getting decremented. So first it was here, then it was decremented by 2 after one push, then it was decremented by 2 after second push. So in this way the stack is growing in this way. So the stack is growing in this way. So my stack is growing from a higher address towards the lower address. So this is called as decrementing stack. Okay, so this is called as a decrementing stack. If the stack grows from here, from lower address to upper address in the reverse order, then it is called as incrementing stack. But here most of the microcontrollers, they implement always a decrementing stack. That is, the stack starts from a higher address, okay, then it goes on decreasing the address, memory address goes on decreasing for the stack. So this is called as decreasing stack. Okay, that is one thing you have to remember. So the stack always starts from higher address. As you go on placing numbers onto the stack, okay, for the push operations, the stack will grow towards the lower addresses. So this is called as decrementing stack. And one more thing you remember is, when the stack pointer will always point to the last number, the last location where the number is present. So this is the most recent number that I have placed onto the stack. So the stack pointer is pointing to the last number where the number is present. Okay, so this is called as full stack. Now suppose the stack pointer is, if it was pointing here, okay, instead of pointing to this location 98, okay, if the stack pointer was pointing to this location, okay, then we would have called it as the empty stack. Now this is stack pointer is pointing to which location? It is pointing to the location number 98 where the last number is present. So this is called as the full stack. So always remember, in MSP430 always the stack is implemented as full descending stack. Okay, it is called as full descending. Full means what? The stack pointer is always point to the last number, the last location where the data is present. Descending means why? What is the meaning of descending? The stack will always grow from higher address towards the lower address. That is the meaning of descending stack. Okay, so this is how the stack push instructions will work. Now for the same scenario, if I write here pop, so if I write here pop, okay, so here I am writing pop and I will write here R5. Now what will happen if I write pop R5? Now this is the current data on the stack. Okay, so stack pointer is pointing to location number 98. Okay, there is some number here. Now when I say pop, what will happen? So the microcontroller will go to the location where the stack pointer is pointing. It is pointing to location number 98. Then it will get this number. Okay, so this number, 6-bit number, will be taken out. Okay, so this number will be placed into this register, that is R5. So R5 register will get this number, that is 15A6. 15A6. So currently stack pointer is pointing to location number 98. So whenever I write here pop, if I write pop here, so this number where the stack pointer is pointing, that number will be copied and it will be pasted into R5. Then what will happen to the stack pointer? So this number has been taken out now by the stack. So my stack pointer will point to the next location where the data is present. Where is the next number present in the stack? It is present here. So the new value of my stack pointer will be this one. So the stack pointer will now point to location 100. Okay, so because this is the number that is next present on the stack. Okay, so every time when you perform a pop operation, the data will be taken out from the current location of the stack pointer. 6-bit number will be taken out. It will be placed into the register that you have popped here. Then the stack pointer will be incremented by 2. Okay, so this is how the stack operations will take place. Okay, in MSP430 microcontroller. So as you can see here, okay, one more operation, one more example is given here. Okay, so this is the stack. This is the starting address of the stack. Already some numbers have been placed onto the stack. Okay, so this is the current location of the stack. Stack is pointing here. Okay, now when I say this push hash 0123, okay, so first the stack will be decremented by 2 first. So it was here, the stack pointer was pointing here, it was pointing to this location, this -2 -4, it was pointing here. It will be decremented by 2 first. It will go to this location. Okay, this starting address minus this, it will come to 2 locations here. Then this data will be placed onto the stack here. 1, 2, 3, 4. Here they have shown all the 16 bits in the same memory location because they are decrementing it by 2 every time, as you can see here. In the previous slide, as you saw, there I had shown you each location individually, but here they are showing 2 to 16-bit locations at a time. Now, so when I say push, stack pointer will be decremented by 2. Okay, it was -4, it will come to -6 stack pointer. Then this 16-bit number will be stored onto the stack. Okay, now when I say pop R8, okay, so where is my stack pointer pointing? It is pointing to this location where the number is present. So this number 1, 2, 3, 4, it will be taken out. It will be placed into R8 register. So R8 will have 1, 2, 3, 4. Okay, then the stack pointer will be incremented by 2 again. So the stack pointer will go to this location where there is the next number of the stack is present. Okay, so this is how the stack operations will take place in case of MSP430 microcontrollers. Okay. The next register here is the register R2 register. So this register R2 is used as, either it can be used as a general purpose register, or it can be used as SR, that is status register, or it can be used as a constant generator 1 register. But usually it is used for what? The status register. Okay. So let us see the contents of the bit structure of this status register. Okay. So as you can see here, the status register is a 16-bit register. So what is the purpose of this status register? So this status register indicates the status of the current status of the microcontroller. Okay, so it is a 16-bit register. Okay, so from bit number 0 to bit number 15. Out of these, only bit number 0 to 8 are used. Only 9 bits are used. The remaining bits are reserved for the future use. Okay, so now let us see which are the different bits that are present in the status register. Okay, so in this, as you can see here, the important bits are bit number 765. So this SCG1, this stands for System Clock Generator 1. So this is System Clock Generator 1. This is System Clock Generator bit number 0, and this is oscillator off. So these 3 bits are used to put this MSP430 microcontroller into one of the low power modes. As if you remember, in MSP430 microcontroller, there are different power saving modes available. Okay, so if I want to turn off some of the peripherals, or I want to consume low power, okay, whenever I don't want my microcontroller to run at full power, full active mode, I can place my microcontroller in the low power mode to save the power. So how to do that? No special instructions are available for placing this MSP430 microcontroller into the low power modes. Just you have to come to this status register, then you have to manipulate these 3 bits so that the microcontroller will be placed into one of the low power modes. Okay, so we'll discuss about this, how to put the microcontroller into different power saving modes when we discuss the clock generator of this, the low power modes of this MSP430. So for time being, you remember that this status register bits SCG1, SCG0, and these are used for putting the MSP430 microcontroller into low power modes. So this SCG1, okay, if this bit is set, this turns off SMCLK clock. As you remember, there are three clocks available in case of MSP430. One is MCLK, the other one is SMCLK, and the other one is ACLK. Okay, so if you don't want to turn on this SMCLK clock, then I can turn off this clock, okay, to save the power by making this bit number SCG1 is equal to 1. So if I make this bit is equal to 1, okay, when set, this bit is set, then this sub master clock is turned off. Okay, if this bit is 0, then the SMCLK will be enabled. It will be generated by the microcontroller. If this bit is 1, the SMCLK will be turned off. Okay, then SCG0, this bit, okay, system clock generator bit 0. So what this bit indicates here, when this bit is set, it turns off the DCO generator. There is internally one digitally controlled oscillator. Okay, so digitally controlled oscillator is there. That generator will be turned off if this bit is set. Okay, if, what is the condition? If the clock generated by this DCO is not used for running the microcontroller MCLK or SMCLK. Okay, if the the DCO is not used for generating MCLK or SMCLK, then if you want to save the power, then you can set this bit equal to 0. At that time this DCO will be turned off. Now if you are using this DCO to generate either MCLK or SMCLK, then you cannot turn off DCO even by setting this bit. Okay, that is a condition. You can set this bit. Okay, you can turn off the DCO only when you are not using this DCO generator to generate MCLK or SMCLK. If you are using this DCO to generate either MCLK or SMCLK, you cannot turn DCO off by making this bit equal to 1. Even if you make this bit equal to 1, when you are using this DCO to generate MCLK or SMCLK, their DCO will not be turned off. Okay, so this next bit, oscillator off. Okay, when set turns off the low frequency crystal 1. Okay, so there is internally during clock generation there is one oscillator that is called as low frequency crystal oscillator. Okay, so if you want to turn that off, you have to make this bit equal to 1. Okay, what is the condition again? This crystal oscillator, okay, it should not be used for generating either MCLK or SMCLK. Just like your DCO, you can turn this low frequency crystal off by making this bit equal to 1, provided this crystal should not be used for generation of MCLK or SMCLK clock. Okay, then there is one more bit, that is CPU off. Okay, so there may be some conditions when only the peripherals are working. I don't want my CPU to be on. So in that case, to save the power, what I can do, I can turn off my CPU. So how that can be done? So if I make this bit equal to 1, if I set this bit, then the CPU will be turned off. Okay, if this bit is 0, CPU will remain on. Okay, then there is one more bit that is called a GIE, that is global interrupt enable. Okay, so this bit is used to enable the interrupts. That means there may be some external interrupts coming from the external world into the microcontroller. So then you can decide whether the microcontroller should accept those interrupts or it should ignore those interrupts. Okay, so when this bit is set, GIE bit is set, okay, so the interrupts are enabled. Okay, global interrupt enable. If we make this bit equal to 1, then the microcontroller, MSP430 microcontroller, can accept the interrupts. Okay, all the maskable interrupts are enabled here by making this bit equal to 1. If I make this bit equal to 0, so when this bit is not enabled, 0 means not enabled, then none of the maskable interrupts will be received by the MSP430 microcontroller. Okay, so that is about these 4 bits: system clock generator 1, system clock generator 0, oscillator off, and CPU off. Okay, then the remaining 4 bits, V, this is overflow flag, this is N, negative flag, this is Z, 0 flag, this is carry bit. Okay, so this overflow flag is used. Okay, so whenever we are dealing with the signed numbers in case of MSP430, okay, so whenever the value of the signed number, it cannot be placed in a single register, then this bit is set to indicate that there is a overflow of the signed number. Okay, so then this negative flag, so what this negative flag indicates, this bit is set when the result of a byte or word operation is negative. Okay, so whenever I perform any arithmetic or logical operation in MSP430 microcontroller, okay, so just remember, in MSP430 microcontroller, the data can be either 8-bit number or it can be a 16-bit number. So whenever I perform any arithmetic or logical operation by using the MSP430 microcontroller, okay, so whenever the operation is carried out on a byte or a word operation, okay, and if the result comes out to be negative, okay, then this n bit is set equal to 1. Otherwise, if the result is positive, then the value of this bit will be 0. Okay, so just remember that. So as you can see here, the data can be either an 8-bit data or a 16-bit data. So if you are using a byte operation, if you are performing a byte operation, if you are working with 8-bit numbers, always the value of this n flag is set equal to bit number 8. That is, if you start from bit 0, it is bit number 7. Always the n bit will be set equal to the bit number 7 of the result. Okay, if I am working with 16-bit numbers, then always the n bit will be made equal to bit number 15 of the result. Okay, so let us see. As you can see here, okay, So here I have written two instructions. Okay, move #12, R4. In case of MSP430 microcontroller, always when I write move instruction, the data will be moved from left to right. So here this 12 will be moved into this register R4. Okay, so the first instruction what it is doing here, it is moving this immediate number 12 into R4. So this 12 will be placed into register R4. Now what is the next instruction? I have written here subtract 13 from this R4. R4 already has what? 12. So 12 is there in R4. Now I want to subtract 13 from this 12. So this is 12. Okay, which is written in a 16-bit binary. Then subtract 13 means 13 should be subtracted from 12. What is the answer? The answer is -1. Okay, the answer is -1. So when I say 12 minus 13, this is the result that is generated by the microcontroller. So the n flag will be made equal to this bit number 15. Okay, so starting from bit number 0, 1, 2 up to bit number 15, the n flag will be set equal to this value, that bit number 15. So when this bit is 0, this bit is 1, so n flag will be made equal to 1. If after performing the operation, if this bit value becomes 0, then n bit will be made equal to 0. Okay, if n bit is 0, that it indicates that the result is positive. If the n bit is 1, that it indicates that the result is a negative number. Okay, here as you can see here, all the bits are 1. That means 12 minus 13 I should get actually -1. But the microcontroller cannot store negative number as a -1. It will store it in the 2's complement format. So this 1 1 1 1 1, this indicates that it is a -1. Okay, so if you convert this number into 2's complement, you will get -1. So how the microcontroller will tell that it is a negative number? It will indicate it by this number, that is n bit will be set equal to 1. Okay, so this is how the n flag is used in case of MSP430 microcontroller. Okay, that is n flag. What about the z flag? Okay, so the 0 flag will be set if you perform any operation on 8-bit or a 16-bit number in MSP430, and if the result comes out to be 0, then this flag is set to indicate that the answer is 0. So if the z flag is made equal to 1, that means the answer is 0. If the z flag is 0, that means the answer is not 0. Okay, so remember. So whenever I perform any arithmetic or logical operation on an 8-bit number or a 16-bit number in case of MSP430 microcontroller, and if the result becomes 0 after that particular operation, then this z flag is set equal to 1 to indicate that the answer is 0. If the answer is not 0, then this bit will remain as 0. Okay, indicating that the result is not 0. Okay, so that is about the z flag. So let us see the carry flag. Okay, the two flags are remaining now, overflow flag and carry flag. So overflow flag. So this overflow flag is very important whenever we are performing the arithmetic operations on the signed numbers. Okay, so you can see here there is an example here. So plus 32767 is written as 16-bit number like this. Okay, then I want to add 1 to this 32767. So decimal 32767 is equivalent to, in binary it is equivalent to this number. Then I want to add 1 to this. Okay, then I should get a positive result here. I should get a positive result here. Okay, so this is a signed numbers. Both these are signed numbers. So how are you going to input the sign of this number? You have to see the MSP bit. So this is 0. This means it is a positive number. Okay, so plus 32767. It is written like this. Then I want to add plus 1. So why plus means it is 0 means this is the sign bit. Okay, 0 is the sign bit. I want to add 1. So whenever I add these two numbers, okay, this is a positive number because it is 0 here MSB bit. This is 0 here. This is also a positive number. So whenever I add two positive numbers here, I should get a positive answer. Okay, 32768 plus 32768. I should get the answer. But what is the sign of the result here? As you can see here, the result is 1. That means it is a negative number. Okay, so this is not valid because whenever I add two positive numbers, I should get a positive result. Okay, but here what is happening here? Plus 32767, okay, plus 1, it is giving me a negative result. It is giving it as minus 32768. Okay, so that is why this is happening here because each register in case of our microcontroller MSP430 is 16-bit. Okay, as you know that the width of the register is 16-bit. What is the highest possible signed number that I can store in one 16-bit register? It is plus 32767. So when I add 1 to this, then 32768, this number cannot be stored in a 16-bit register. That means the positive number that is generated out of this operation, addition operation, is greater than the number that can be stored in a 16-bit number. That is why this overflow flag is set to indicate that there is a overflow of the signed number. Okay, this is how the V flag should be interpreted. So whenever you are working with the signed numbers and if the V flag is set, then you should understand that there is the signed number overflow. The result is not valid. You should interpret it like that. Now let us see the details of carry flag. Okay, so this carry flag is used to indicate, okay, that a result is too big to fit into the target register. So as you can see here, there is one example here. Okay, so there is one 16-bit number here. This is another 16-bit number. I want to add these two. So whenever I add these two, okay, if you go on adding bit twice, okay, I will get this result. Okay, 16-bit answer I have got, but also I will get a carry here, output carry. Okay, so carry is generated. So that means the result that is generated is actually a 17-bit result. Okay, including the carry, but only these 16 bits are stored in the register, and since there is a carry generated, the MSP430 microcontroller will set this carry flag indicating that a carry has been generated. Okay, that means the result is greater than 16 bits. That is why to indicate that the result is greater than the 16-bit register, okay, then the carry flag will be set by the microcontroller. Okay, so this is about the carry flag. Okay, then there are two more bits. Okay, in the register file, if you see, there are two more registers, that is constant generator 1 and constant generator 2. Okay, so these constant generators CG1 and CG2, they are used to generate some constants. Which are the constants that are generated by this CG1, CG2? 0, plus 1, minus 1, plus 2, plus 4, plus 8. Okay, so these 6 commonly used constants are generated, okay, with the constant generators registers. R2 is CG1, R3 is CG2. Okay, without requiring an additional 16-bit word of the program code. Okay, so whenever you are writing any instruction in MSP430 microcontroller, and many times I want to use these numbers in the instruction. I want to move this number plus 8 into one of the register. I want to move this 0 into one of the register. So at that time, what I have to do? I have to use these numbers in the instruction. Now, when I use these instructions in these numbers, integer numbers in the instruction, okay, these numbers will also be stored in the memory. While executing the program, what the microcontroller has to do, it has to fetch these numbers from the memory into the registers for execution. So in order to save the memory, also in order to speed up the execution, since these constants are used frequently, the microcontroller will generate these numbers automatically. Whenever you are using these numbers in your program while writing the instructions, okay, these numbers will be replaced by these registers. Okay, so that is the purpose of these two registers, CG1 and CG2. So we'll study about this CG1 and CG2 in detail when we are dealing with the instructions of the MSP430. So for time being, you remember that this CG1 and CG2, they are used to generate 6 constants. Which are the 6 constants? 0, plus 1, minus 1, plus 2, plus 4, and plus 8. Okay, so these numbers, constant numbers, will be generated with the help of these two registers, R2 and R3. R2 is called as CG1, constant generator 1, R3 is constant generator 2 register. Okay, so we have seen the details of the program counter. We have seen how the stack pointer can be used to access the stack. We have seen the different bits of the status register, which indicates the status of the current status of the MSP430 microcontroller, and we have seen the constant generator CG2, okay, and CG1 is here, that is this one, R2. Okay, now the remaining resistors are what? From R4 to R15, they can be used as general purpose resistor, that is for storing the data. Okay, so as you can see here, okay, so if I write move #6, R4, okay, this 6 will be moved into R4. Okay, place the number 6 into register R4. Then add #9, R4. That means add this immediate number 9 to R4. So like this, from registers R4 to R15, we can use them while writing the program. Okay, so this is how we can use the different registers of MSP430 microcontroller. Okay, thank you.